All right, so there are two parts in building the bridge that I want to talk about. There is the design, the actual engineering of it, and then there is the construction, which is making it happen, okay? So in the design, there are a lot of the elements that we use in the statics class to actually put into the design. So I want you guys to say out loud some of the things that you guys think of. So we have free body diagrams. We have some of the forces in X, some of the forces in Y, some of the moments. What are some of the things you guys think you could use?
Make sure we don't have any zero force members.
Good.
You could use shear and moment diagrams.
Perfect. Shear and bending diagrams. Anything else you guys can think of?
Find the reaction forces.
Good. Reaction forces, and then I will add compression, tension. Okay, so if we draw a bridge, we have it across the top, and then we have two bases on the bottom. The most important part of design and construction is that these loads meet where your beam comes up here, okay? There are 5 loads that come down, and in the past, instructions have been wrong, but the correct instruction is, it's about 30, I think, what is it? It's like 28%, and then like 17, something like that. So it's about double in the middle what it is at the end. I know that there have been instructions that show that the end are the heaviest, but these aren't the exact numbers, but this is the right distribution where it's heaviest in the middle. So the most important thing is that your beams line up perfectly with these loads. Okay? So typically there's the 6-beam design. So let's draw that. Okay, and then we have reaction forces. So there are 2 ways that you can solve for these 2 reaction forces. You can make these loads percentages out of 100, or you could set your goal weight and then figure out based on the percentages the actual load in pounds that will be coming down. Then once you solve for the angles, you can actually determine the compression. Oops, I do those backwards. Backwards again. You can solve for the compression here inside of these beams. What are the advantages of knowing the compressive forces, the loads that each of these can bear?
Also, it's not the strongest material on the planet, so it can only take so much before it snaps or it just gets crushed.
Yeah, you could Google like the material,
That's the strength.
the strength of balsa wood. You can determine that. But you're also going to know which beam is going to take the most load and which beams that you need to beef up with the most balsa wood. Whether you do a 5-beam design or a 6-beam design like this, you can calculate the actual compressive force and say, okay, this one and this one is going to be way bigger because it's a bigger load, so we need to make these thicker. They're also longer. They're going to be a little more bendy, and so it's going to break here. We need to beef those up. So based off of your compressive loads and your reaction forces, you can strengthen your design and the construction as well. The other thing that was mentioned is the shear and bending moment diagrams. Okay, so if we took just a shear diagram here, and then you can calculate the exact numbers, but if we start at 0 here, it's going to go down, and then depending on where this is, it's going to go back up, then down even more, then back up, and then down, something like that. where you can, and this is just a sloppy example, but you can figure out where the most shear force is going to be, and again, you can strengthen those beams. Same with bending.
So just a quick question, you drew those like as a distributed load, aren't they just point lines?
Oh, you're right.
Okay, just want to make sure.
It's been a while since I've done these. So that would be, it goes down off the back, and then it would go up, and then down again, and then down again, up, down, down. Yeah, you're right, it's gonna look something like that. And then that's going to be, if this is all right, down, then up, then down steeper, then up. Yeah, so it doesn't work out based off of me eyeballing it. But you get the picture of where you can calculate where the greatest moment is going to be and the greatest shear force based off of your diagrams from calculating this. So going back here, I want to talk about calculating the optimal distance here. Okay? How can we calculate this from the end here? Where to place these, making that long, making these shorter and stronger, or putting it closer over here so it's a straighter beam under this load. What do you guys think is the best way to solve for these distances? And are they equal? What are your thoughts?
Distances between like the forces?
So from the end, how far in do these legs go?
You probably want it to be symmetrical, because if the force is going down or symmetrical, you want it all to be balanced.
Good, okay, so they're gonna be equal, so they're both X's. Other thoughts? I think this is the most important part of the design, because based on where this goes, this is where the sum of the moments is going to be equal. So if we take a point here, right, we have a line of the force right here, another one right here, another one right here, another point here, and these forces go down. So we have moments that are being created at these points, and like you said, they need to be equal. So I'm not going to tell all of the secrets, but try and figure out a way where you have 2 points, you have a symmetrical beam, where can you take cuts, where can you make it so that the sum of the moments is equal to 0. That's where you're going to have the strongest design, is when you can figure out this distance so that the sum of the moments about this point, we'll call this A, is equal to 0. And that's the biggest secret in building the bridge. Okay, so you can draw free body diagrams to do the compression and tension at a certain point. Take a free body diagram there or here. Zero force members, let's talk about that. Are any of these 6 zero force members? No, right? But you'll see some bridges that will have, I don't know, maybe something like this, maybe something like this, maybe something like this. So we'll talk about this one. Zero force member?
Yeah.
Yep, this one?
Yep.
Yep, this one?
Yep.
Yep, that one. Okay, they're all zero force members right there. What are advantages or disadvantages to these? Is this one any advantages?
Negative.
Yeah, not really any advantages. What about this one?
Keep it from snapping in the center.
Good, because these beams are in compression, they're going to buckle out, right? And so if we put a beam in there, it's going to prevent buckling, but it's not going to take any load. What about this one?
Kind of the same idea.
It could be the same idea. I wouldn't recommend anything like that, because if anything, looks like you'd be pushing down on it and bending it up that way. And so there is a strategy to using zero force members, but they have weight, and your bridge has to be under a certain weight limit. What is that weight limit? Is it in the instructions?
I want to say 30 grams, but I'm not, that's just off the top of my head.
Yeah, so it needs to be light. You'll be pretty close using all the material in the packet to that weight, but you're gonna have to keep it down. The last thing you wanna do is be like sanding down your beams the morning of. Okay. Another little secret here is the maximum height. The rules will say, but I think it has to be less than 6 inches, but greater than 5 inches. So the height's going to change your length, it's going to change the way your moments work, it's going to change the distance. And so choosing a height is the first step, and then calculating your angles and then your moments and your distances and stuff like that. But one tip is the shorter, the less material you're using, the more you can beef them up and still be underweight. And so one trick is to make this as short as possible, but keeping it in the range of the rules. Reaction forces, compression, tension, zero force. Okay, the last thing in design is your beam. So in class, you talked about I-beams.
They haven't yet, that's this week.
You will talk about I-beams this week, and you'll learn about the moment of inertia, and then you can compare that to just a regular square beam. Now, remember, you'll learn that I-beams are more efficient, which means you're using less material, but you can get almost the same kind of strength. So you have to decide as the engineer, what kind of efficiency do we want? Weight versus strength. Right, so this has 6, 7, 8, this has 9 beams. So this one's gonna weigh a little more. Is it gonna be stronger? You can do those calculations using moment of inertia. But I will tell you that in theory is different than in construction, right? So if we were using welded steel, it's different than using balsa wood and super glue, because these are only connected on one tiny side of balsa wood and glue, and right here. Whereas this has 3 sides of glue connected. So this, as an aggregate whole, is going to be stronger than just one piece glued together, right? So you have to, again, weigh out the pros and cons and the costs and all that. Okay, I think that's all of the theory that is used in statics that goes into the bridge. Any questions so far?
I have one.
Yeah.
The most common question is, which way does the I-beam face?
I don't remember I-beams all that well in moment of inertia. I never used the I-beams. From what I understand, the I-beams will face, how do I draw this? That the I-beam is on the inside here, that this is a flat side, and then inside you have that I-beam like that. Is that right?
I'll talk to him about it.
Okay. I'll go back and study it. I didn't take that. I'm taking that FE on the 18th.
Congratulations, Nate, well done.
So I need to review those. Okay, so now going to construction, which if you have the most perfect design in the world and your calculations are no errors, they're perfect, and then there are errors in construction, it doesn't matter what you've done in design. It's completely wasteful. So if you cut your beam and it actually will end up right here, and you miss the load, it's completely worthless. So the biggest part of construction is cutting the wood. Now, I would glue your beams together, right? And so maybe at the top of a beam you have a bunch of uneven balsa wood that looks kind of like that at the top of your beam, and then you draw the line at the angle you want to cut it, and then you get the right tools. If you can get like a table saw or even a bandsaw and cut those, the straighter, the crisper, the cleaner, the better. And so finding the right tools, maybe it's worth a Facebook post or some phone calls trying to find the right tools so you can get these cuts flush with the top, right? An easy way to do it is to get like a big poster board or even maybe a whiteboard, and then you draw your design on the whiteboard, and then you lay your wood on top of the whiteboard, and then you just, with a pencil, you draw your line on the wood, and then you put it through the saw and get them all cut. Now, you're not going to want to procrastinate gluing. If you glue the night before, your glue is not going to be cured by the time of breaking. And so, when it comes to gluing, did I spell that right? Is there an E in gluing?
That's good.
You want to glue well in advance, at least, let's see, probably at least 2 full days before you'd like it to be pretty much done. Then you can put in a little bit of glue in the gaps where you have extra left. But gluing at the joints is going to be extremely important. So the cuts at the joints, gluing at the joints, the way you organize the space at the joints, those are all important. And really it comes down to whatever you think is best. You can, no, how do I say this?
Craftsmanship.
Yeah, the craftsmanship's extremely important, but also logic. You know, if we take this and we tip it at a bird's eye view, so here's the base, they have one beam come in here, another beam come in right here, and then the third beam come in right here, right? That's all that's pushing back, because you have an X force, an X direction force right here. All that's holding it is the glue friction that's pushing that X direction back, right? And so if you can line up your beams like that, then you have the force pushing this way and that way, and glue is no longer essential. So actually, it's still important, but it's not the only thing that's holding these two together. So don't be too creative in building this. I mean, it's pretty straightforward in just being logic and thinking some of the forces need to equal 0. Any other questions? That's pretty much it.
Is it a 2D or 3D bridge? Like, is it just like a single plane type of bridge, or is it like a full bridge?
Yeah, so it's just in the y direction of these forces, right? And so, yeah, it's 3-dimensional, but it's only like a ½ inch thick.
Right,
maybe.
that's what I mean. Like, we're not making like a full like solar box across the bridge. It's like.
Would you like to see a kit? So the machine that comes down is a hydraulic press, and it has 5 pins that come down, and they hit this top